Hello again. Once again, this video is sponsored by Autodesk, and I'm going to carry on a little bit more with locations. So I'm going to make I've made a sphere there and a plane. So I'll just make the plane a little bit bigger, like that, and slightly more subdivided. And I'll move this sphere up above the plane. Okay. Now, what I'm going to do is duplicate that plane so it's topologically identical and stick it over there. And what we're going to do is a little trick. It's not really a trick. Well, no, it kind of is. To make this sphere read the locations, the closest position on this one, and then show that because locations are basically like, you know, each point's going to find a polygon, and where it is on that polygon, I think they're called barycentric coordinates. Barycentric coordinates, and it's to do with weighting, not waiting like waiting around in a bus shelter. Weighting as in like between the points, so it knows. Oh, I don't know how they're stored. It's stored basically at I don't know why I keep going on about this, but it's yeah, a location is basically, it's a way of identifying where it is on this surface, and because this surface is the same as that one, you can swap it over to fool it into thinking that it's dealing with this one as well. So let me I'll do it because it makes more sense if I just do it rather than waffling on about it. So I'm going to create graph, grab the sphere, grab that plane, and then grab that plane. So we get the sphere's point positions, get point positions like that. From the point position, we want to get closest locations. So we're looking, the locations we're looking at are from these points. So we stick the points in there, and we want to look at this mesh, which is that one. Okay, and then at the locations, at those little identified polygon things, we want to sample property. Okay, so we're sampling the property on this mesh. We want to find point position, see down here, which the default, that means default means type, as far as I can tell, is a float 3. In other words, it's an XYZ coordinate, it's a position in space. So that sample data is now, say there's 300 points on here, we're getting 300 bits of data here, all on the surface down here. The point positions of where they are, where they're hitting on the surface. So we could use that to set point position of this mesh, and it will go burp. Oh no, burp, there. So the BIF is now squashed on there. But the cool thing about locations and doing it like this is that we could actually, because this is out of here is coming a little identifier of where it is on the surface for each one. Because this is identical, we could plug this one in and say sample those positions, which is this one is, of this mesh, and it will go burp, and it will go over there. So I think that's quite cool, because you can use that as a basis for doing like cage deformers or other stuff. And yeah, that's just something that's worth knowing about locations. Now, if I wanted to make this thing, this ball 3D instead of on the surface, what I would do is, right, so let's stick it back on that original one, so it's going on there. So between each point here and where it hit on the surface, that's going like down on the y-axis in this particular scenario. And if we got those amounts and we projected it back up from when it's here, we'd have a sphere again. So we've got the positions as they are here, and that's the original one. We've got them here, that's when they were squashed down here. So to get the difference between them, we subtract that lot from that lot. No, not that lot, because that's when they're there. From them. Okay, we're going to need another sample, because we're going to need to know where they were when they were here. So we need to sample this one and do a subtract there. Okay, because this one's no good, because then we'd be going from the points to there, which is no good. We want the points to that one, which is this one now, because it's plugged into this mesh here. Okay, and then, but out of this node is coming the same positions here. So if we added them back, so added this to that lot, like that, then it goes, see, it goes back again. Now, it doesn't work entirely, well, it does work like that, but it doesn't work if I do this. Because, you know, they're still, those vectors aren't changing direction, they're just still going like there, they're just going upwards. So we end up with it going all squashed and flat, you know. To do it so that it always sticks outwards from here, you need to do some more jiggery pokery, which I'm not going to do in this video. But anyway, that's something else to know about locations, which is handy, that you can sample, you know, you grab your locations here, but you can sample other bits of geometry that are topologically identical. They have to be the same. You could sample something else that's a sphere, but you know, well, shall I try it? It's going to look ridiculous. So I'll bring the sphere in and I'll sample. So we're grabbing the, this might get confusing. I'm grabbing the locations on here, and then I'm going to swap them over to here. Now ice wouldn't let you do that for the following reason. Because, you know, because its topology isn't organized in the same way, you're ending up with something that's a complete and utter nonsense. But I like the fact that you can do that if you wanted to. But, you know, I'm just demonstrating that to say it's a bit of a stupid thing. Because the indexing of these points is not the same, you know, the indexing and the layout of these points is not going to be the same as that. So that's where you end up with a thing that's mathematically correct, but is, you know, doesn't really make any visual sense. So obviously if you move this sphere around here, that one moves the same, because it's, you know, it's finding different locations and that sort of thing. So in terms of locations, you can do get closest location, and that is finding the it by how close it is. Other ways of finding locations are raycasting. I went through this in another video, but I just thought I'd go. So get raycast locations, which is basically, you know, you tell it the position it's starting from, you know, like on this one, the positions, but you can also give it a direction, and instead of just getting the closest, it will point out like in whatever direction you point it in, like the normals, and then you can, then from then on it's the same, you just sample whatever you want on this mesh. How long have we been going? Well, I'm going to improve this system to try and make it so that if I do this type of thing to this object, or even something like this, that it will properly react, you know, to the you know, the ball will kind of not do that, but it will sort of stick out relative to the surface. So it's a kind of like a cage deformer, a simple kind of cage deformer effect, rather than just projecting upwards. So now this is going to get slightly more complicated, because what I'm going to do, I'll get rid of that, So these are all the bits that I've got so far. Let's spread this out a little bit more because I'm going to need more space. Okay, so getting those locations, getting the properties, and we're doing all of that as I did in the last video. What we're going to have to do is, as this surface rotates, so that one's pointing up, this one's pointing there, we want to be able to project these. This is sorry, let me just this is where the vectors are projecting out from, and we want to be able to rotate these so that they are going out, as this surface turns, that they're going out like that. So we need to check the angle on this surface, and use the difference between that one and that one to be able to rotate those vectors, which were pointing there, like directly vertically here, and are also pointing vertically here. Instead of making them vertical, we want to be able to rotate those vectors around, and that's this bit here, going from this pipe to that one there. So first of all, I'm going to stick rotate by quaternion there. And then we need to make a quaternion. Quaternion is basically a rotation that will rotate those vectors properly. Now, it's not doing anything at the moment at all. That's sort of like not valid because we don't have anything pumping into that quaternion. So we need to make a valid quaternion rotation. And to get the difference between this surface rotation and that one, basically what we need to do is get the point normals from this one and the point normals from that one. That will give us something that gives us two dimensions, but it doesn't give us a third. And the reason why that is if you're familiar with like direction constraints, it also needs an up vector. So a point normal doesn't give us an up vector. We need to get something that's sort of relative across the surface. So we've got up and down, but we need a cross as well, and that will give us a full kind of thing that describes the full rotation between that surface and this one. So we're going to get the point normal. Now, to do that, we have to get another one of these that grabs the point normal. So, oops, don't do that. I go here and I change that over here to point normal. Normal. That's getting us the point normal. And so that's from that original plane. We need to do the same on this plane. So I'll copy that one and change that to point normal. Oops, not normal position. Let me just type that in properly. Point underscore normal. Okay, what I'd like to see actually is a drop down list here of all the properties rather than having to type it in. I'm sure that will come at some point, but that would make life a lot easier. So we've got the position, we've got the point normal. The other thing we need to get is a line across the surface. Now by default, there is, if I look on here, there is nothing like that. We've got the point position, point normal. There's nothing. What it is called is a tangent. Basically, we have to add that. So it doesn't exist by default, but we can add it by going tangent update face tangent. Now if we stick that into this object here and stick the out going into these, basically what's coming out of this object now contains another property, so we'll hook that one up as well, which has that face tangent. So if I do a little watch point after here, you'll see that it has, well, on one that's actually hooked up. It doesn't evaluate it unless it's actually hooked up at the other end. So if I zoom in here, you see now it has this face tangent, and that is like it's like you know, the normal is perpendicular to the surface. This kind of runs across the surface. It just sort of calculates, and it's consistent between this mesh and that topologically. So if this one was at that angle, the tangent is always, you know, it stays relative to the, you know, the mesh itself, like topologically. So now on this, I don't understand what this means, but you have to stick this on UV tangent space on both of these. Again, I don't know what that is, but you need that on, and we need to sample also now that face tangent. So face tangent, and do that with this one as well. So face tangent, oops, tangent. Okay, so it's sort of looking slightly more complicated. Hang on just 1 second, let me just pause this. Right, sorry about that. Oh, sorry about that. You didn't have to wait because I pressed pause. I had a package delivered. Okay, so we've got the normal and the face tangent, normal and face tangent, and we can use that to quaternion from not direction up vector, although I don't see why that wouldn't work, but that's not the one I use. It's tangent, normal and tangent to orientation. I don't know why the terminology is different there. This is part of the Rebel pack. So we get the, so what have we got there? We've got the normal and the tangent, and we'll do it on this one as well. So normal and tangent, and that gives us two rotational, two different rotations. One that represents each location's rotation on this point of the surface, so like the normal and an up vector, and its equivalent down here on this one. So we need to find the difference between these two and rotate that by it. So to get the difference between these two, we need to invert, quaternion invert, and then multiply quaternions. Now, it doesn't matter if you don't understand this, but I'll try and explain it in another video. Basically, that's a process of finding the difference between this rotation, which is the one we're looking at originally. You invert it, and then you multiply it by the one that you want to make it go to. So if I plug that in, hopefully this sphere will pop out that way. It might not, because I have a feeling I could have done something wrong here. Hey, no, it did work. Okay. So this BIF now is, you know, it's projected that where that one is relative to this surface, this one is now relative to that surface. So even if we warp this surface by doing something like this, it's gonna be stuck to it. It's like a wrap deformer rather than a cage deformer. And obviously, you know, if you move this one around, it's still relatively, you know, this one stays relative to it, moving on that curved surface at any different angle. This is cool, for example, for having clothing sticking to a body, you know, or belt buckles or things like that. I use this all the time in my stuff. But I also wanted to show that, you know, people look at this and I've had quite a few comments going, you know, it's not a very fast workflow. And I wanted to show that if I wanted to make a wrap, if I wanted to use this effect in Bifrost, I wouldn't do this. I wouldn't go, oh, I'll get point position. I would be doing this. So I'd go, I'd make this thing here, and I would only make this compound once. So I did Control G to make this thing here. I'd call this wrap. I'd call this one mesh to deform, something like this. I keep double clicking on things because that's the ice way. I'd rename this from, or from geo, and I'd rename this to geo. Okay, so next time I want to do it, I just bring in 3 things and plug them into this and plug that into that. The process is, you know, I get this compound, I plug these things, so this is how long it would normally take. Like, I just showed you how to build a wrap deformer, okay? Not how you need, what you need to do every time you want to use a wrap deforming effect. So basically the workflow would be like this. I click on the wrap, I bring that up, I'd have it in here, I'd click on wrap, this would pop up, I'd go burp, burp, burp. Okay, like that. And that's it. So it's not a slow, okay, why didn't that work? Oh no, it did work, sorry, it makes the biff, yeah. Okay, so it's not a slow process. You know, there is a confusion with some people between how long it takes to build a tool, how long it takes to do this bit, which took me, you know, maybe 20 minutes, which I don't think is bad for building a wrap deformer, and how long it takes to use the final tool. Now you can adapt this tool as well, like you could have this so that, you know, it blends between the original points and the wrapped points, or, you know, all sorts of stuff you can customize into this. But that's a basic wrap deformer, and, you know, doing a compound is not, you know, making a compound is not the same as using a compound. And I just wanted to make that point because I've seen a few comments about that, as if the workflow is incredibly slow compared to doing it up here, and it really isn't that slow because, you know, as I say, it's just a matter of plugging stuff into it and reusing compounds. Cool. All right then, that's it.